Let's return now to MapReduce and ask where the data that MapReduce programs require is taken from and where does the output go. Clearly, MapReduce reads and writes fresh data, right? As we've seen before, it's a batch process. The question is, where does it read this data from and where does it write the output to? Even if MapReduce is a parallel computing paradigm, what about the data read and write? Does that form a potential bottleneck? The solution is that the data itself needs to lie in a distributed format, whether it's a distributed file system or a database, so that we can support parallel reading and writing, so that more than one processor is active reading or writing a large file. Otherwise, input and output itself will become a bottleneck for the MapReduce parallel computing program. Further, we've discussed processing node failures and seen how MapReduce recovers from these without letting the overall MapReduce job fail. But what if the nodes on which data is stored fail? They also need to be fault tolerant. To solve both these problems, distributed file systems were developed primarily first by Google and then Yahoo, and that's what we're going to study next. This diagram illustrates the architecture of the distributed file systems, both the Google file system as well as the Hadoop distributed file system, which is open source now and is essentially the foundation of what is big data technology wherever it's used. Whether there's a database built on it or used directly, the HDFS is fundamental to big data. This is how it works. Large files are distributed into chunks, typically of 64 megabytes in size, and each of these chunks is stored on what are called chunk servers. Further, chunk servers are replicated so that each chunk is stored on 3 different servers, typically replicated on multiple racks and in a different network subnet to take care of all types of hardware failures. As a result of this replication, the possibility of data being lost due to hardware failure is minimized significantly. Of course, the challenge is now to maintain consistency across all these replicas. So here is how that works. When a client application, say a MapReduce program, needs to read data, it needs to first figure out where a particular piece of data resides. A read command typically is issued with a file name, which is a path in a directory structure, and an offset, that is how many bytes ahead in the file the client wants to read. Data about what parts of a file are on which chunk server is kept in a master node, which is called the master in GFS, and it's called the name node in HDFS. And the client reads the metadata from this master node. The metadata tells it where the particular offset that it is asking for resides, that is, which chunk server. The metadata itself is cached by the client when it first starts reading so that it doesn't continuously have to go and ask the name node or the master for information. Further, while actually reading data, the client directly contacts the chunk server, which is listening for such requests and serves up requests for particular chunks of data from a file, rather than go through any centralized system. So if there are many clients reading a large file, typically they will be accessing different chunk servers, and therefore these reads are happening in parallel. As a result, input at least doesn't become a bottleneck in a parallel MapReduce job. In case the reading client, that is, say, a mapper, fails to contact a chunk server, it looks up the master data to figure out where the next replica is stored and tries again. Since there are 3 replicas, the chance of all of them failing is fairly low, and that lends fault tolerance to the input-output process. Of course, the tricky part comes in writing, because while writing data, we have to make sure that each replica contains the same data all the time. Here is how writes happen in GFS. Of the 3 replicas for each chunk, one is designated as the primary replica, could be any one, and that information is kept in the master. Of course, the master keeps pinging these replicas to make sure that they are alive, and in case the primary is down for some reason, the master node assigns a new primary and possibly even asks for a new replica to be created for that chunk. Now, when writing data, the client application sends the data to be written to all 3 replicas for a particular chunk. One of them is primary, and it figures out where to write this data, assigns an offset to write the data, such as typically the end of file, and sends this offset to the other 2 replicas. If these replicas succeed in writing at that particular point, they tell the primary that they have written, and the write succeeds, with the primary informing the client that the operation has successfully completed. On the other hand, if some of the replicas fail to write at the designated offset, which can happen, for example, because of a bad disk sector, then they return a failure to the primary, and the primary retries to write at another offset, could be beyond the end of the file, for example, and tries again until it succeeds at all replicas. As a result of this process, large bulk writes can be done in parallel on a large file by multiple processors, typically reducers, writing the output of a MapReduce job, while still ensuring that 3 replicas of every chunk are maintained synchronously and with the same state. GFS and HDFS are the foundation for all big data technology. GFS, of course, is proprietary to Google and is internally used. HDFS was developed at Yahoo and open sourced as part of the Hadoop distribution, and has now become synonymous with MapReduce and large-scale computing using big data. So to summarize, what the GFS distributed file system architecture is really good at is supporting multiple parallel reads and writes from a large number of processors. The reads are arbitrary and random access, but the writes are best done when they are appends, or writing to the end of a large file. Because the architecture relies on the primary replica for a chunk deciding the order in which multiple append requests are processed, the data is always consistent, though not necessarily predictable in terms of which processor's data is written first. That normally doesn't matter because the data is fairly independent, especially in MapReduce output. At the same time, it's important to realize that random writes in the middle of some file, while can be handled using the GFS architecture exactly the same way as we have described, are not as efficient as bulk writes towards the end of the file. Imagine a large number of reducers writing their output to a file which will eventually become large. As soon as a reducer decides to write, say, a 64 MB chunk, it has to figure out that this is going to be a new chunk and inform the master or the name node that it's writing a new chunk. Similarly, other reducers figure out that they're writing new chunks and inform the master. The master updates its metadata, and all the writes happen in parallel. The master does become a bit of a bottleneck, but because the writes are fairly large, that doesn't normally create a problem. On the other hand, if we have random writes to the middle of a file, the challenge then becomes what happens when a chunk essentially overflows and impinges on another the next chunk in the file. This can create problems in the way the file is laid out and requires much more synchronization. Without going into too much detail, it's also shown in the paper on GFS that the degree of replica consistency that one gets with large bulk appends is much stronger than the degree of replica consistency that we get with random writes in parallel. Nevertheless, even with a reduced degree of consistencies, each reader in the GFS architecture always sees a consistent data regardless of which replica it ends up reading from. That's one of the powers of the GFS architecture. Still, GFS and HDFS, while supporting bulk parallel reads and writes, are nevertheless file system architectures and not databases as we have come to understand them over the past 30 to 40 years. Much of the current debate in the big data and traditional BI communities is about databases. The big data databases are built on top of distributed file systems like GFS and HDFS. But before we turn to these, let's first take a look at traditional databases and see why they were developed and how they've actually been used